Welcome to the main memory chapter. So, a little background here to remind you that programs are passive entities. That they must be brought from disk into memory and put within a process for it to be executed. So the main memory and the registers that are built into each core are actually the only storage that the CPU can really access directly. And the CPU has to fetch the instructions from memory according to the um, value that is written in the program counter. Remember the program counter? It always saves the next instruction to be executed by the CPU, and so the CPU has to load that instruction from the memory. So these instructions in turn may again cause some more loading and storing operations again from memory.
So we can think of main memory as our workspace or a working desk. Just like this desk provides us with a temporary and accessible space for us to store and manipulate the current task, the main memory serves as a fast and temporary storage area for data and instructions that the CPU needs to actively work on. So similar to how we organize our desk to keep only the important documents and tools within reach, main memory does the same. It has to organize and store data in a way that allow the CPU to quickly retrieve and manipulate the data. So just like us, when we put all the extra documents and extra tools that we have that we don't need currently for the current task, we put them away in drawers or cabinets. We can think of the secondary storage like the hard disk drive or SSD as that drawer or those drawers or those cabinets. That's where we keep all the extra files and documents that we don't need fast access to for the current task, whereas we only keep the data and tools that we need for currently for the current task for fast access and retrieval. We put them in main memory. So the main memory acts as a bridge between the CPU and the long-term secondary storage devices, such as hard drives or SSDs. And so just as the desk that provides us, just like our workspace or the desk that we sit on that provides us a convenient space to work while still allowing access to files that are stored in those shelves or drawers. And so just like our workspace or disk, it has a limited space, right? We can only put a limited amount of tools on it. Same thing with main memory. It has a finite capacity. It can hold a certain amount of data and instructions at any given time. And once it reaches that limit, then some information has to be moved out to accommodate new tasks that come in. Just as a person, it may sometimes need to clear the space on the disk by filing away completed work. We put it aside and we remove the unnecessary tools that were done using away. So main memory is a very important component in our system. Therefore, we have to protect it. And so the protection has to be done via using hardware support, because the OS does not like to be in the middle between the CPU and the memory access operations, because this will cause some memory degradation. So how can we ensure protection instead? So the way we can provide protection is using the base and limit registers. So we say that we assign to every process a legal space of addresses that this process can legally access, and it falls between a base address and a base plus limit address. And so the process can freely access all the addresses in this area, but if this process tries to access an address that's outside this range, then a trap is generated to the OS saying that this is an illegal access. And so the CPU has to check every memory access that is generated in the user mode, make sure that it falls within the base and base plus limit range, and then if it's not, then an error is generated because of that. And so the instructions to just load the values of these two registers, the base and limit, are considered to be privileged. Okay, it can only be executed under kernel mode. So addresses can be represented in many different ways at different stages of the program's life. So it starts with the symbolic representation of addresses, and that's when we're still at the source code level. And so when we say, for instance, the variable counter, so counter is just a symbolic address. Okay, so once that code gets compiled, then those compiled addresses actually bind into relocatable addresses. And so relocatable addresses are seen with respect to the beginning of the object file. So we kind of say the address is 14 bytes from the beginning of the object file, or 16 bytes, and so on. And then the linker or the loader will then bind those relocatable addresses into the final absolute addresses in the main memory. So the address binding to absolute memory addresses can be done at three different levels. Either at compile time, where you already know the absolute address where your program should go or your data should go, then if you do know that information in advance, you can do the address binding and provide exactly the absolute address at compile time. The other alternatives is the binding can happen at load time or finally at execution time. So the advantage of execution time binding is that the program can start at one, can be allocated one initial address, absolute address at the memory, but then while executing, the program has the freedom to move to a different location in memory, and that can happen for different reasons that we're going to discover today. But that movement cannot happen if we already specify an absolute address at compile time. So here we're going to make the difference between two address spaces. Okay, so there is the logical or the virtual address and the physical address. And so when we say space is the set of addresses, okay, so the virtual space then will be the set of all the virtual addresses that a process can access, and the physical space will be the set of all the physical addresses that the process can have. So the logical address is what the CPU generates in user mode, whereas the physical address is the actual address that is seen by the memory unit. So what's a memory unit? So a memory management unit, or MMU, is the hardware device that at runtime does the mapping of the logical or virtual address to the actual physical address. So there is many ways to do this mapping, and that's what we're going to talk about next. So another quick note here about dynamic loading and linking. So we don't need the entire program to be in memory in order for it to execute. So for instance, when we are doing error handling and we have some error routines or functions, we don't need to load them until we need them, right? And that for memory space, for better memory space utilization, right? We do not need to load those unused routines that may never get to be used actually, right? So one solution is to keep those on disk in relocatable load format, and then we only load them when actually an error happens. So that's dynamic loading. And then our program may actually have multiple modules, and then sometimes we also link some other libraries or system libraries. Sometimes we may end up never use. So instead of linking them all in the beginning before execution, we can do dynamic loading where we only do the linking and loading of any module or any library code when actually we need it, okay? And that's during execution. So this will improve memory utilization in a way that we don't have to load and link everything in the beginning before execution, and then we end up not using most of it. So this will hurt the memory utilization and make us allocate space that ends up being wasted. And so the opposite of dynamic linking is static linking. So with static linking, a function f is loaded into memory when? Is it when the main program is loaded, or when the program calls f for the first time, or for each time the program calls f at runtime? So with static linking, we said that with this approach, we do have to load everything at once before execution, okay? Which means that everything is loaded into memory when the main program actually is loaded. So the opposite is dynamic linking. The function f will not be loaded when the main program is loaded, but actually when we do need and we do call that function f. And so if we have concurrent processes P and Q that share that function f, then so if both they call function f, then we do have just one copy in memory and they both share it. And so again, if we have P and Q that share a function f, but none of these two processes call f, but we are using static linking, that how many copies of f, there's still going to be one copy in memory, even if none of these two processes actually called f, because static linking is used. So that function has to be linked before execution. Now, in case we are using dynamic linking now, and none of the processes called f, then there will be 0 copies of f in memory. We do not actually need to load f until it is being called.